Good afternoon to one and all. And today concept is about knowing the type declarations in intermediate code generation. And before knowing how to represent the type declarations in intermediate code generation, first of all, we need to know what the forms of three address code statements are. Here, the forms of three address code instructions can also be called it as in types of three address statements. Make a note of this, types of three address statements. And here, see, I already recalled, I explained the forms of three address instructions in the last classes. Just I'm recalling what the language constructs were having and how to write the intermediate code form for that language construct. Right. And coming to the assignment statement, here the language construct is an assignment statement. And for the assignment statement, how the intermediate code form representation is, how to write an intermediate code representation is x is equal to y object. And x is equal to of y also comes under the assignment statement under the language constructs. And x is equal to y, there here we're using an assignment operator. That means copy statement. This comes under the copy statement. And go to L. Go to L is an unconditional jump. And conditional jumps are if x go to L and if false x go to L. If x rel of y go to L. These two are the conditional jumps. And while coming to the go to L, this is an unconditional jump. And all these are the language constructs. For the language constructs, how to represent an intermediate code form. That's what we're learning here, right? And today concept is about a declaration statement. If you know the representations of the intermediate code forms for any type of a language constructs, then it is easy to learn the concept like in type declarations. So that's why I'm again recalling the concept like in forms of three address instructions, or it can also be called it as an types of three address statements. And here the next one is about an procedural calls. For example, my language constructs are in the form of an procedural calls. And here the intermediate code form, the writing of the representing the intermediate code form is param x call p comma n, y is equal to call p comma n, so on. And for representing an array statements, my language construct is in an array statement. So I'm using x is equal to y of I and x of I is equal to y. These are the three address code form representations that we can also call it as an intermediate code forms. And finally, to represent for the addresses, to represent for the address or for the pointers, pointer assignments, we need to use the forms like an x is equal to ampersand y and x is equal to star y and star x is equal to y. Right? Is it clear what the representations are? These are the intermediate code form representations. That means types of three address statements. We're naming it as in types of three address statements. And just what I done here is, what I explained here is just I am giving the language, what language construct it is. So for that language construct, which type of intermediate code form we need to represent, right? So I explained that. Now I explain for the language construct and the representation of an intermediate code form. Is it clear? And what it means is the form of the three address code is very much similar to an assembly language. So here some commonly used three address codes for typical language constructs are used. So I explained all those commonly used three address codes for typical language constructs. And now going to the today's concept about type declarations. The concept is about type declarations. Once all of you see the slide that I shared to you, what the slide consisting of? The slide consisting of some statements. The statements means production rules, some set of production rules. Those production rules are from the given grammar, right? And here my production rules are in the form of an in the sense it is in the form of an a tends to alpha, right? A tends to alpha. What it means is every rule is in the form of an a tends to alpha. Now, by taking such type of an productions from the given grammar, how we are representing the type declarations here. How we are representing the type declarations. And this example comes under the declarative statement example. Why? Because here the data items along with their, see here in the next slide I will explain. The data items along with the data types are declared here. Make a note of this. This is nothing but an a storage layout for the local names. And this is the by using this example, I will briefly explain how to declare the type declaration statements, right? That means in declarative statements, the data items along with the data types are declared. What it means is, here, by considering the given grammar, my grammar consisting of some set of rules. In those set of rules, T tends to BC, B tends to int is an terminal, make a note, B is an, B tends to float, int, float, num, all those comes under the terminals. And in the same example, in this example only, I'm having an num in the error representation, num in an error representation. That means whatever we represented in a square brackets, that defines that it is an array. That defines that it is an array. And here I am using an attributes with an type and width. Two attributes I am using here. Both two attributes I assigned for each and every node. That is b dot type, b dot width, b dot type, b dot width, or c dot type, c dot width, like that. And here, from the example, this is the example that we performed the computations for the types and their widths. Here we perform the computations for their types and their widths. And what it means is, what we are doing here is, first initially we need to define the attributes. We need to define or assign the attributes to the nodes. And then we need to compute. And then we need to compute. From the grammar, C tends to num C1, where num is an array. Num is an array. That is num dot val. The value of the lexical analyzer is assigned to a num. And that is assigned to the C1 dot array. And what it means is, here we're multiplying these two. Here we're multiplying the num with an C1, and whatever the resultant we're getting, that resultant is associated to an C, where C is an C dot width here. And here what I'm doing is, I know what the syntax director definitions are. I know how to write the semantic actions for each and every corresponding rules. So with the knowledge of that, here what I am doing is, I am writing the semantic actions. That means I am defining the syntax directed definition, and here I am implementing the semantic actions corresponding to each and every rule. And here in every rule, the rule consisting of the nodes. Nodes means a non-terminals and the terminals, right? That every node should be assigned with an attribute values, type and the width. Here I am using two attributes, type and width. These are the two types of synthesized attributes. One is an type and another one is an width. And here, whatever the terminals that I am getting here, that I am generating from this grammar, are in the form of an int, float. All this comes under the basic data types, right? So I am choosing the attribute as a type here. That's why I'm choosing an attribute value as a type here, right? And here I need to perform some computation. So I am choosing another attribute as an width. So this is the way of writing and semantic actions for the corresponding production rules, where T is equal to T. What T is T type for T, small t, width for W, right? T is equal to B dot type, W is equal to B dot width. And what B dot type is, it is an integer, and just I am giving an integer value 4 here. And what B dot value, it is float, and that is B dot type is equal to float. The basic data type here we are using, it is a floating point, right? A float data type. So the B dot width is assigned with a floating point value 8. It is an integer value 4. Make a note of this. And if it is C tends to T, that means if for the C, if C is a node here, that means it is a non-terminal. For the C, I am using the two attributes, like a type attribute and a width attribute. So I am assigning the both T and the W to the both C dot type and the C dot width. And here I am performing in computation. See, all of you, performing in computation, I am writing in function here, function for the array, where what the function, why I am creating this function means, here in the right hand side of the rule for the C, I am having the array representation for the num. So array of num. So for that I am using this function, array of num dot val, comma C1 dot type. What it means is, whatever the value that I am computing here, that is assigned to an C1 dot type, right? Now after getting what the C1 dot type, then I need to get the value for the c dot width. I need a value for the c dot width. So how I'm getting that value? By performing these two, that is num dot val. Num it itself is having a val as an attribute. That's from the lexical and lexical, that is from the lexical values, from the lexical analyzers, where taking from the lexical analyzers that num dot val and into c1 dot width, right? After performing this computation, whatever the value, whatever the number we will get, that is assigned to the c dot width, right? Here we get b dot width, and c dot width, right? And t is for t dot type, and I think it is clear to you all, and how to write the semantic actions, and whatever the action that we enclosed, whatever the statement that we enclosed in an braces like this, that can be called as a semantic action. That what the meaning of that is, writing of these braces, what the meaning of that is, this is a translation schema. This is a translation scheme. With a semantic action, we performed or we implemented a translation schema for the corresponding production rule. Is it clear? Now, this is an syntax directed translation of array types. You all know what the arrays are. What the arrays are? Array is a collection of contiguous storage of elements, right? And why we are using these arrays? For accessing any elements, in an array, what we need its addresses is, we need its address, right? So here this overall, by seeing this overall tree structure, what it means is it seems like an annotated parse tree. It just seems like an annotated parse tree. Why? Because here the every node is defined with its attribute and the values computed at the nodes, right? And here only we are showing that which is an inherited attribute and which is an synthesized attribute, which is an inherited and which is an synthesized. And the values computing from the parents or the siblings can be, it is an inherited, right? So it is an inherited and it is also an inherited, and this inherited value is assigned to this C, and this is acting as a synthesized attributes. That means here computing the values from the child nodes, that's why, and from this C to this C and this C to this C and this one to finally the root node of the tree, that is an T, where T is the starting node of the given grammar. This is the representation of an annotated parse tree for the syntax directed translation schemas, whatever we performed in a previous slide. For the previous slide, this is a representation, right? And next, here I'm going to explain about how the sequences of declarations can be done. See, it is a declarative statement because the items along with the data types are declared here. What it means is, one see the semantic actions, that means these are all comes under the translation schemes. Why? Because when we enclose it with the braces, then that can be called it as a translation scheme. Here we performed a semantic action, and that action was, whatever the action we performed here, that action is associated with is enclosed with an braces, right? So this can be called it as an syntax translation schemas. And from where we get this? We get this from the syntax directed translation. And after implementing the syntax directed translation, why we implemented the syntax directed translations? Here we're having the two ways of representing the semantic actions, right? The first way is syntax directed definition and the second way is syntax directed translation schemas. So here in the sequence of declarations, we are implementing the syntax directed translation schemas. So whatever the semantic action that we enclosed in the braces, that can be called it as a syntax directed translation scheme. That means there itself we performed the translation, right? So we're showing like this, we're showing the representation like this. And initially from the, by taking the grammar and from the set of rules under the grammar, initially the value of offset is set to 0. Make a note of this. The value of offset is set to 0. What it means is the computation of offset can be done by using the formula like offset is equal to offset plus T dot width. What this T is, and T is a node here. T is a node. So in the abort translation schema, T dot type and T dot width, these two are the synthesized attributes, right? These two are the synthesized attributes. That means the type indicates the data type of the corresponding identifiers, and width is used to indicate the memory units associated with an identifier of corresponding type. For example, here in the previous slide, we're having the values like it is 4, integer has width 4, and the real has or float has an width 8, right? So this is an example that these are the instances. For instances, we're taking those as an examples. That means type and width. And here coming to this sequence of declarations, and we're having a rule like D tends to T ID semicolon. And it is a declarative statement for the ID declaration. ID is an identifier, right? And here we're having a function. What that function is, enter tab is a function. By using that function, what we're creating is we're creating the symbol table entry for the identifiers along with its type and offset. Make a note of this. And the width of the array is obtained by multiplying the width of each element by the number of elements in the array. Is it clear now? In the previous slide, I explained what it means. The width of the array. I need an width of the C, width of the node C. So the width of array is obtained by multiplying the width of each element by number of elements in the array. By the number of elements in the array. And here the width of the pointer type we didn't have any pointer types here. And if we are having any pointer types from the given grammar, and there itself by computing such a function, then we can get an value, and we can define that it is supposed to be some n is an some value, the width of that particular pointer type, right? Is it clear how the sequence of declarations are defined? And this is from the declarative statement. And today my concept is about an type declarations, right? In that, this is the most important concept, sequences of declarations. Knowing about the sequences of declarations, then we have to know how the assignment statements can be defined. That means the assignment statements mainly deals with the expressions. Make a note of this. Mainly deals with an expressions. And the expressions can be of any type of a basic type. It may be in type, integer, real, array, and record. And here we're having two types. One is in basic and another one is in constructed data types. And here we're merging those basic and the constructed data types here. When we're implementing such type declarations, so we're merging them. That means record, array, all those comes under the constructed data types. Int, float, double, char, all these comes under the basic data types, right? And here uh, we're writing the syntax directed translation schemes for generating the 3-address codes for assignment statements containing the arithmetic expressions, or for any type of constructed data types. Here I'm having the both basic data type and the constructed data type. See, if one see the slide that I shared to you all, and what the slide is about the fields in records and classes. What the fields that are consisting of in the records and the classes. Records and classes, these two are the constructed data types. And by taking an example, float x, float is an basic data type, right? Float x, record, float x, semicolon, float y. And this is a constructed data type, and the after recording this, after implementing the record data type, then the value is to be stored in an P. The value is to be stored in an P. And once see the third example, record int tag float x, float y, and whatever the thing that was associated, that was enclosed in the braces. This is, see here, we're having, this is a record. Record is a constructed data type. To which data types we are going to construct this? For int, for float, I'm constructing this, and the resultant is stored in an queue, right? And here I'm having the production rule from the grammar. T tends to record D. Here I need to record D. How to record this? how to record this. T again, it is having an as attribute with an type, dot type attribute and record. And when we are performing this record data type, that means when we are implementing this record data type, we need to use the stack. We need to use the stack. That means you need to perform the push and pop operations here. Performing push and pop operations. That means initially the stack is an empty, right? So the offset is 0. Offset is 0. And after you are recording the top as an t dot type and t dot width is an offset. Now after initializing the offset is in 0, then I am assigning this offset with an t dot width. Then finally what I need to pop here. Finally what I need to pop here. And what the value of what I'm assigning to this offset. This offset is stack dot pop and top is an, again it is an pop, and t dot type is assigned with an record of top, t dot width is assigned with an offset, right? And this is the way of writing the semantic actions or implementing the syntax directed translation schemas for the corresponding production rules. And here translation of expressions and the statements. And what it means is the assignment statements comes under these translations of expressions and statements. And for example, just by taking an example, I explained the sequence of declarations in type declaration. And we already discussed the translations to intermediate code was already discussed. Type checking was already discussed at the concept of semantic analysis. Type equivalence, type system, type conversion, all these are all, I just define what and what it is and how to convert. If we are using a type conversion, how the conversion takes place or what the type equivalence consisting of. All those are explained in the concept of the semantic analysis. So here, at the concept of translation of expressions and statements, one of the concepts that we can consider under this is one assignment statements we're considering here. Along with the assignment statements, in the previous slides itself, I explained the type declarations, and there itself I explain you how to define the offset of the variables. That means I discussed all these topics, right? And what the next is 3 address codes for the expressions. 3 address code for the expression. See here we're having an example. For this example, the translation scheme which in turn will generate the 3 addresses code. What it means is all those are the production rules, and here I am defining the semantic actions or the semantic rules, and finally we're calling them as an, here these are all not the translation schemas. Why? Because nothing, no action is enclosed within braces. In the semantic rules, no action is enclosed with the braces. So we are just calling them as an semantic actions or semantic rules corresponding to the production rule, right? If we enclose it with the braces, then that can be called it as a translation scheme. Make a note of this, translation scheme. And here how the semantic actions are written here, and S tends to ID, where ID is equal to E. See here we are using two attributes. One attribute is an code and the another attribute is an address. That means every node is defined with an attribute. Here every node is defined with an attribute at the semantic actions, at writing of the semantic rules. S dot code, E dot code, E dot address, E dot code, like that, right? Finally, from the rule number 1, what we need to generate, what we're going to generate. What we're going to generate means we need to get ID for, we need to get an ID where ID is a lexeme here. That ID is assigned to an E because E is a node here. E is a node here, right? So when I'm computing something, the value of the computations takes place, and where I'm storing that result in, and I'm choosing another variable for that, right? So this E dot address is for storing of the result of the performer computation. So from this statement, what we are generating is this one, and E1 plus E2. initially e dot address, we need to use this new temporary functions. We need to use like this because e dot address is a new temporary function. While writing for the e tends to e1 plus e2, right? So when we are writing for the attribute like in code, the way of writing or the way of representing the semantic action is e dot code is equal to e1 dot code or e2 dot code. There we need not to bother about the terminals. Here also s dot code is equal to e dot code. But when we are generating the output with by using with an attribute address, addr is an address. Then we need to write e dot address is equal to e1 dot addr plus e2 dot addr. That again for the e we are having e1 minus e2 minus e1 open parenthesis e1 closed parenthesis id, right? So again we need to write a new temporary function for the e dot address, and we're having another rule, right? Minus e1, and for writing an attribute for the code, e dot code is equal to e1 dot code. And to generate an output in the address attributes by using with an address attributes, then e dot address is equal to minus is there. No, here we're considering the operators also. But when I'm writing for the attribute of the codes, there itself we are not considering the attributes, right? Minus e1 dot address. And here the terminals, we're not taking the terminals like an open parenthesis and closed parenthesis. Just e dot address is equal to e1 dot address and e dot code is equal to e1 dot code. For the two attributes, we're writing like this. Finally, id. id is the id lexeme, right? Because it is a terminal and lexeme from the lexical analyzers. So the resultant, this should be stored in an left hand side of the variable e. That means it is the address of this lexeme. So e dot address is equal to, we need to get id dot lexeme. So for writing of the attribute like an code, nothing is there. Nothing is there to write for the attribute code. So it is null. Nothing is there, null. So you should left out like this. Don't write anything in between the quotations. Just it is nothing there. Nothing is there to represent. Nothing is there because e dot code is not assigned to any type of non-terminal. So we're lefting like this. Don't write anything. And this is the way of writing the semantic actions for the three address code expressions, right? Is it clear now? And then it is an incremental translation, and just it is a simple difference between this three address code for the expression and the incremental translation. What's the difference in these two concepts is, here we're only considering a single attribute. In previous example, we considered two attributes. One is for code and another one is for address, right? And incremental translations were performed. See here, it is a translation schema again. It is a translation schema. Why? Because here I enclosed the action with this type of parenthesis, right? So this can be called it as a translation schema. What it means is, here we are not writing an attribute for the codes, only for the addresses. Only for the addresses we are writing we are implementing the translation schemas and naming that it is an incremental translation schemas. And what new temp is the function for generating the new temporary variables, right? The function new temp is a function for generating the new temporary variables. And whatever the functions append is for appending the three address code to the output file. Otherwise an error will be reported if you use a function like an append. But here we didn't use any function like an appends, right? And what this id.lexeme means, it lookups the entry for the id.name in the symbol table if it exists there. If not, it's just an lexeme. If not, it's just an lexeme, right? And if you're having like e dot address means is used to hold the value of the e. This e dot address is used to hold the value of the e, right? Is it clear now how to write the translation schemas in an incremental translation? And this is the way of writing the translation schemas. If you understand the three address code for the expressions, and without writing the attribute for the codes, directly we're writing for the address attributes. We are writing for the address attributes for each and every non-terminal here. And this is the way of writing the semantic actions, calling them as a syntax directed translation schemas where corresponding to each and every production rule from the given grammar. Right? Is it clear? Then, now the concept is about an arrays, addressing array elements. As we all know, array is a collection of contiguous storage of elements. For accessing any element of an array, what we need its addresses, right? And here where statistically declared arrays, it is possible to compute the relative addresses of each element. Typically, there are two representations of the arrays. If you all see the slide, then you can easily understand. The first way of representation is an row major representation. The second is an column major representation. These are the two representations of the arrays. What the row major and what the column major representations is, here in the rows we are using first row and second row. In the columns we are using like first column, second column, and the third column. And we need to compute the addresses of every element. Whatever the elements that we are using here, we need to compute the addresses of any element. What it means is initially we need to know the base. Well, here it is a two-dimensional array. Once all of you see the slide, it is a two-dimensional array. What it means is we need to consider I and j subscripts. That means considering row major representation will compute the relative addresses for a of ij. What a of ij means, I and j are the subscripts. A of is nothing but a two-dimensional array representation, right? A of 1, 1, A of 1, 2, 1, ij, like that. All those are the representations of an array. And initially, to compute the addresses of any element, first we need to know how to compute the base. And how to compute the base means the base addresses is at A of means an array, and W is the width of the element. That means it is in required memory units. Then we need to compute the ith addresses of A of I. That means base of I minus low into W, where low is a lower bound on subscript and A of low is base. And what this base is, how to compute this base. And if you know the computation, if you know the formula of the base, then only we can calculate the array of ij. Then only we can compute the array of ij. That means the array of ij is having the formula for the performing the computations of addresses of any elements, like A of ij is equal to base of I minus low 1 into n2 plus j minus low 2 into w. What it means is, here we need not to bother about the formulas and the computations, because we are not doing the problems, just we are knowing what the array elements are, how to address the array elements, that's it. And what this low 1, low 2 are the two lower bounds on values of I and j, and n2 is the number of values, and j can take values that j can take. That means if sometimes you can also take that n2 is an high 2 minus low 2 plus 1. High 2 minus low 2 plus 1. So these are all can be computed in terms of the base. But no need to bother about the formulas, just to know how many types of representations are there. For having two types of representations, one is in row major and another one is in column major. And how to represent those, just by drawing these structures, we can lay out an two-dimensional array. And initially we need to define what the array is. Array is nothing but a collection of contiguous storage of elements. And for what's the need of using this array is, for accessing any element of an array, what we need is, here we need its addresses. So is it we are declaring static or dynamic, means always we're declaring in a static array, statically declared arrays. That means if you declare statically, then only the arrays are possible to compute the relative addresses of each element. Then make a note of this. This is the most important point. For statically declared arrays, it is possible to compute the relative addresses of each element, right? And these are the things that you need to know. Other than this, no need to worry about the computations or what the base, what the formula of the a of ij. All this we need not to bother about this, because we are not solving any problems or we are not doing anything. Just knowing about what the context in the addressing array elements is, how to represent an row major and the column major, right? And the next concept is about semantic actions for array references. After knowing what the definition of the array, now we are writing the semantic actions for the array references. See, here my grammar consisting of an array at L tends to ID of E. At L tends to ID of E. Everything is same. Everything is same in incremental translation and the 3 address code for the expressions. But here what's the extra thing that we're going to learn in this concept is the name itself, it is there here, the semantic actions for the array references, right? So I'm choosing that directly. I'm going to the production rule. L tends to ID of E, because these are all I explained in the previous slides. L tends to ID of E. What it means is L dot array is equal to what I need to get. I get an ID dot lexeme, right? And here I am using 3 types of synthesized attributes. 3 types of synthesized attributes, that is L dot array, L dot type, L dot address. Finally, what I need to generate? I need to generate the L dot address is equal to E dot address into L dot type dot width. Right. To generate this, I need to write the translation schemas for the array, for the type, and for the address. Right. Again, I'm saying that new temp function is nothing but an generating new temporary variables. Function used for generating the new temporary variables. Right. And here also I'm having L1 of E. Here also I'm using the 3 attributes from the synthesis. So these are the 3 synthesized attributes: L dot array, L dot type, and L dot address. Finally, what I'm going to generate here, initially I'm generating an T, where T is an here I'm performing the computation between the E and the L dot type dot width. And after getting the value of this T, then that is used for adding to the L1 dot address. Finally, I am generating L dot address. And these are all the semantic translation schemas for array references. In the previous slide, for the incremental translation and for the 3 address code for the expressions, I explained you how to write the translation schemas or the semantic actions, right? See here, for a non-terminal L, it has 3 synthesized attributes: L dot address, L dot array, L dot type. These are the 3 synthesized attributes. Dot addr is an attribute type. Dot array is an attribute type. Dot type is an attribute type. And then here we're having a concept like conversions between the primitive types in Java. There are 2 main conversions. One is a widening conversion and the second one is a narrowing conversion. Widening conversion means it does not have any directed path. Just in linear, just where just using with an line representation, just where showing that from the double, from the float and long and in short, char, byte, like that. But while coming to the narrowing conversions, here with the direction path we are showing. With the direction path we are defining the primitive data types in the Java. So how we are defining the primitive data types in Java means conversions between the primitive data types in Java means there are 2 types of conversions here. One is widening conversion and the second one is a narrowing conversion. Coming to the representations, these are the 2 ways of representing the widening and the narrowing. And while coming to the example of introducing type conversions into expression evaluation, that means from the conversion I am evaluating from the expression what the type it is. Just I'm introducing here, right? See once E tends to E1 dot E2, right? The left hand side of the variable is an E, and the right, whatever the computation that I performed with an operator plus with E1 and E2, I'm getting a value. That value is assigned to an E, right? So here I'm taking an attribute as a type attribute. I'm choosing an attribute, that is for every node I am giving an attribute like a type, and along with the type I'm using another attribute, that is an address, ADDR address. That is here for the non-terminal E, I am using 2 synthesized attributes. One is type and one is address, right? And here I am converting. I am using the conversion of an widening conversion. Widening conversion I am using here. That means I am evaluating the expression into an widening conversion. And E dot type is equal to max of, because I am performing an addition operation, right? Max of E1 dot type comma E2 dot type. And I am assigning an variables like A1 and A2. A1 for the E1 and A2 for the E2. And that means here I am implementing the conversion, widening conversion here. Widen of E1 dot address, E1 dot address, E1 dot type, comma E dot type. Is it clear? That means for the variable, for the node E1, I am using the two attributes, and that is stored in an E, right? So E was already assigned with an attribute type. E was already assigned with an attribute type. So E1 dot address, E1 dot type, E dot type. For the same as it is for the E2. For the E2, I need to use the two synthesized attributes, address and the type, and it was stored in an E. So E is already defined with an attribute type, right? So E2 dot address, E2 dot type, E dot type. And finally, again here E dot address is a new temporary function. And finally, what I'm going to generate here, E dot address is equal to A1 plus A2. What A1 is widening conversion of this. What A2 is widening conversion of this, right? And where I'm going to store this, the resultant is in an E dot address. That's what I'm generating here. And what I did here, I write the semantic action for the corresponding production rule. When I enclose it with a parenthesis like this, then it comes under a syntax directed translation schema. Then it comes under a syntax directed translation schema. That is it clear up to this concept? And this concept, that abstract syntax tree for the function definition, I will explain this in the next session. The tomorrow class, I will explain the abstract syntax tree for the function definitions. I think you all understand the today's session about the type declarations and the representations of the semantic actions, and along with the syntax directed translation schemas.